The Real Science of Time Travel, with me, Dr. Dan Stokes. Part 1. Breaking Time. What if you could rewind one moment, literally move to an earlier point on your own timeline? Time travel sounds like science fiction, yet modern physics already lets us do parts of it. We can travel to the future by changing how fast our clocks tick. The real question is whether we can ever come back. In 1905, Einstein merged space and time into what's known as spacetime, and discovered that it is all relative. The key factor in this determination is what's known as the Lorentz factor. According to this equation, if your velocity approaches the speed of light, then the Lorentz factor approaches infinite. What that means is that your traveller's clock runs slower compared with someone who stands still. Let's look at some real examples of that. If you were to travel at 80% of the speed of light, then for you, 1 year would be 1.6 years compared to someone standing still. If you were to travel at 99% of the speed of light, then for you, 1 year would equal 7.1 years, someone standing still. If you were to travel at 99.9999% of the speed of light, then for you, 1 hour would equal 707 hours of someone standing still. This is not speculative, it is measured daily. Some other examples. In 1971, the Haffel-Keating experiment showed that when 4 cesium-133 atomic clocks flew around the Earth, those travelling eastward lost tens of nanoseconds, whilst those travelling westward gained hundreds. This matched relativity to within experimental error. GPS satellite clocks in medium Earth orbit tick differently from ground clocks due to both speed and gravity effects. Special relativity slows the satellite clocks by around 7 microseconds a day. General relativity speeds them up by around 45 microseconds per day. This is a net increase per day of around 38 microseconds. This has to be pre-offset, otherwise your sat-nav would drift off by kilometres every day. Every position fix is a demonstration of relativity. So, time travel forwards in time is just time dilation, and we can amplify it fairly easily with velocity. Einstein's 1915 field equation relates mass energy to curvature. This means that a near non-rotating spherical mass, gravitational time dilation, slows clocks. The closer to the mass, the slower the time. An extreme case of this is black holes. At the event horizon, the factor of this equation tends towards 0, as seen from infinity. This means that for the local traveller, time is well behaved, but for distant observers, their clock appears to crawl. How is this portrayed in sci-fi? Well, in the film Interstellar, 1 hour was equal to 7 years on Miller's planet. To get such a ratio, you would need a gravitational potential and orbital speed near a supermassive black hole with a large spin according to Kerr's geometry. So tidal forces that were seen on the film would be survivable. The numbers in this film are aggressive, but they're not nonsense, they're real. The mix of gravitational redshift and orbital velocity can, in principle, create multi-hour per year dilation effects. This is therefore a good example of a sci-fi film that gets the real science correct. What about wormholes, shortcuts through space-time? Einstein-Rosen bridges, as wormholes are otherwise referred to in physics, were first proposed in 1935 as real wormhole solutions. In 1988, Morris and Thorne asked a sharper question on wormholes. They asked what metric would allow a human-safe, traversable wormhole. The answer required violating the average energy conditions for a human to traverse a wormhole. You would need a negative energy density in the throat of the wormhole. This is a bit of a problem. 2 conducting plates separated by around 1 micrometer can exhibit vacuum mode suppression and produce real negative energy, but only at a density of around 10 to the minus 3 joules per cubic meter. This is astronomically too small. If we needed a wormhole that was actually survivable and human safe, around 1 meter wide, wide enough for a human to pass through, we would need energy densities of around 10 to the 42 to 10 to the 45 joules per meter cubed. This is an immense amount of energy. If you were to annihilate the planet Jupiter and acquire all of the energy of that annihilation, that would be around 10 to the 44 joules. How about making a time machine from a wormhole, though? If you take one end of a wormhole on a relativistic journey while the other remains stationary, the two ends would desynchronize via time dilation. Step through the younger mouth and exit the older mouth of the wormhole, and you would emerge in the past relative to your departure. This is perhaps the sharpest physics solution for a genuine time machine. However, it does require that exotic negative energy matter that we don't yet know how to accumulate macroscopically. So what about paradoxes? There are plenty of these in science fiction. There's the grandfather paradox. This is where you create a contradiction by altering your own ancestry, killing your own grandfather, for example, resulting in you never having been born. But if you're never born, then you can't travel back and kill your grandfather, so he lives, and then so you live, and then you travel back, etc., etc. There's also the bootstrap paradox. This is where you deliver a future artifact to the past, and change time such as the object is never created. It therefore has no origin, and therefore can't be taken back in time in the first place. Real physics has some resolutions to these paradoxes. There's the Novikov self-consistency theory. The maths here essentially says that events can't create contradictions. The maths itself forces self-consistent outcomes. The other major resolution is what's referred to as the many worlds theory. Any alterations spawn a decohered branch. Your original history and timeline is unchanged. There is no paradox, just branching. In one branch, your grandfather is killed, and the other he is alive, allowing you to travel back. Some physics essentially states that time can only travel in one direction. Microscopic laws, such as Newtonian quantum unitary evolution, are time reversal symmetric. Yet macroscopic phenomenon show an arrow. Entropy increases as time progresses. The universe started in a very low entropy macro state and is constantly becoming a more disordered state. Human beings' perception of time is thermodynamic too. Memories are physical records. Record making increases entropy. Therefore, even with a perfect time machine, your subjective arrow would persist because cognition is dissipative, i.e. your memory would only work when time is flowing in the direction it currently is. Forward time travel is ordinary physics. Extreme dilation via speed or gravity is allowed and measured. Backward travel requires some sort of exotic matter. Spacetimes we don't yet know how to engineer, or quantum mechanical consistency mechanisms that probably forbid paradoxes or route you into a new branch. The real science doesn't prevent time travel. It's just behind a mountain of energy, engineering, and maybe even nature's own chronology protection mechanisms. In part 2, we will examine what will be required for practical time travel, and we'll also take a look at time travel in popular sci-fi franchises and examine which get the real science correct and which don't. Until then, check out my other videos, and if you like them, subscribe.